Constraint satisfaction problem. So we'll see another type of problem solving algorithm, which is called constraint satisfaction problem. Now let's see what happened in this particular problem. So in this particular topic, we'll describe a way to solve a wide variety of problems more efficiently. Here we are looking for more efficient solution and more efficient than alpha beta pruning, because in the alpha beta pruning we have seen like we can remove some of the part of the tree which will not going to affect our final results. Now here in constraint satisfaction based problem, uh, we are going to introduce another factor which is called constraint here. And based on the constraint, uh, a agent can move and find out what is the suitable move or what are the legal move. So it is based on the constraint. And let's see this particular constraint satisfaction problem. It is very interesting problem and very simple problem to understand. This topic describes a way to solve a wide variety of problem more efficiently. We use a factored representation for every state. In every state, we'll use factor representation. And in this factor representation, we have two things. One is the set of variable, and each set of variable is associated with some value. So we have variable and its value pair that is there with every state. The problem is solved when each variable has a value that satisfy all the constraint. Now here, the problem, whatever the problem has been given, it will be solved when each variable has a value that satisfy all the constraint on the variable. It means we have given the constraint forehand, means when we want to solve the problem, the constraint has been given, and based on the constraint, every variable should be associated with some value. Okay, every variable is associated with some value because this is a variable and value pair. So a problem described this way is called a constraint satisfaction problem. Now in this constraint satisfaction problem search algorithm, it will take advantage of the structure of the state. So whatever the state we have and whatever the structure we have in the state, as well as uh, it will use the general purpose rather than problem specific heuristic. Here we'll use general purpose heuristic, not the problem specific heuristic, to enable the solution of the complex problem. Now all the complex problem could be solved, means many of the complex problem we can solve with the help of constraint satisfaction problem. Complex problem in the sense where the complexity is exponential, is n to the, there is 2 to the power of n. In that type of problem complexity, whatever problem we have, we just have to go through these type of problem solving method so that we can actually solve them very efficiently. The main idea is to eliminate large portion of the search space all at once by identifying variable value combinations that violate the constraint. So whatever the value variable combination is violating the constraint, we just remove those portion and we'll eliminate it. In that way we can actually reduce how many we can reduce the space complexity, as well as at a very efficient way we can find out our solution to that particular problem. So let's see in the next next slide. Here we have some definition regarding constraint satisfaction problem. It is very important to understand. A constraint satisfaction problem consists of three components. So we have actually three components here, which is X, D, and C. So we have three component in the constraint satisfaction problem. The first component is called x. X is nothing but set of variables. Okay. D is nothing but set of domain. Domain means the value that will be given to the variable is called domain. Means let's say if we have a variable x and we have variable y, and x has all value which is odd and y has all value which is even. So you can see that all the even value is for x and all the odd value is for y. So this odd value and even value is nothing but the domain of that particular variable. The last one is C. C is the set of constraint that specify allowable combination of values. So we'll allow some of the combination of value based on the constraint. So constraint is based on two variables or three variable, whatever variable we have, it is based on that. Now, if you see this, you can understand very well. Each domain di, if we have a domain di, it consists of a set of allowable value v1 to vk for variable xi. So in each domain, we have some value which is allowable. It means, let's say if I'm talking about x and y as a variable, x is taking all the value which is even, and y will take in all the value which is odd. So the domain of x will be all the value which is even, right? So the value even is which is divisible by 2. So maybe it will start with 0 or it start with 2. Or you can say that domain of the y, it will start with, let's say 1, 3 in that way. So you can very well understand what is the meaning of that. Now each constraint has been given. It consists of a pair. So we have a pair, we have a scope and the relation, scope and REL relation, where scope is a tuple of variable that participate in a constraint, and REL is a relation that defines the value that those variable can take on. So you can see we have, first we have learned, we have two things, variable and value. Variable will be associated with each value, and value are nothing but allowable value based on the constraint, right? So we have mainly three things, x, d and c. Based on that only all the this constraint satisfaction problem will be defined. A relation can be represented as an explicit list of all tuple of value that satisfy the constraint, or as an abstract relation that support two operation. Test if a tuple is a member of a relation and enumerating the member of a relation. So here it is talking about relations, so that how two variable will have a relation and how they will work on the relation. And this relation is nothing but the constraint, and based on that constraint only the value will be allowed on to the variable. So this is the idea behind this constraint satisfaction problem. If we'll take an example, we have two variable x1 and x2, and this x1 both will have the domain a and b. Let's say both will take a and b. So we have x1 which also can take a and b, and x2 which also can take a and b. So we have a variable and the domain. It means we have values also. Then the constraint says that the two variable must have different value can be written. Now what is the constraint? Constraint here is, if we have two variable, then at a time both the variable should have different value. It means if we'll take x1 as a, so for x2 we have to take b. We doesn't have any option. If x1 is taking b, so x2 will take a. We doesn't have any option, because constraint says that both these two variable must have different values. So how we can represent it? We can represent it in that way: x1 comma x2, which is nothing but the scope, and this is a relation. It says that either you will have x1 will have a and x2 will have b, or x1 will have b and x2 will have a. Or we can write in that way also, that we have a scope, and scope is x1 and x2, whatever the variable we have, and both are not equal to each other. So this is a type of relation they have. So this is scope, this is relation. To solve the constraint satisfaction problem, we need to define a set. We need to define a state space and the notation of the solution. So here we should have some state space and the notation of the solution that we have to define. So how we'll define it? Each state in constraint satisfaction problem is defined by an assignment of value to some or all the variables. So what we do is we assign some values, because this constraint satisfaction problem is factored value. In each node we should have a variable and we should have the value associated with that, and we should assign this particular value to the variable. An assignment that does not violate any constraint is called consistent. So any assignment which is not violating the constraint, it is called consistent or legal. A complete assignment is one in which every variable is assigned, and a solution of constraint satisfaction problem is nothing but consistent and complete assignment. Means whatever variable we have in the problem, each variable should be assigned some value, and all those values should be legal. All those values should be consistent. Means all those value we have picked up from the domain would satisfy the constraint. Then only we get the solution in constraint satisfaction problem. A partial assignment is one that assign value to only some of the variables. So when we talk about partial assignment, it means some of the variable does not allow any value. So for that, it is called partial assignment. So as I told you, the constraint satisfaction problem is all based on some constraint and the game theory, as we have seen previously. This is a Sudoku game. I think most of you have played this game. So what is this game is? Here we have how many boxes are there? Here we have around 81 boxes are there, and this particular square is divided into how many? This cluster of 9 boxes. So we have 9 boxes of cluster here in this particular box. In each particular box, small box, in a small box, we should have the value from 1 to 9. In each box, we should have the value 1 to 9. This is one constraint here. What is the second constraint? The second constraint is in each row, if we have the value, that value will not going to repeat it. As well as in each column, if we'll get the value, that value is not going to repeat it. Means if we'll got 9 here, so 9 will not come here in that particular column. And if we'll have 3 here in this particular row, so 3 will not come into that particular row, right? As well as in each boxes, we should have the value from 1 to 9 and it is not going to repeat. This is the constraint. What is the variable here? Variable are nothing but the boxes. Whatever the boxes we have are the variable. What is the domain? Domain is nothing but the value. What value we have? 1 to 9. So 1 to 9 is my domain. So we have variable, that is these boxes which are empty right now. We have domain which is 1 to 9, and we have constraint. What the constraint is? In each box, in each small boxes, we should have the value 1 to 9, and each column, if we have the value, if it is coming, that value will not going to repeat. As well as in a row, if value will come, that value is not going to repeat. So based on that, we perform this particular problem and we'll solve this particular problem. This is one example of constraint satisfaction. Let's see another example of constraint satisfaction, which is called map coloring problem. You might have gone through the map coloring problem in algorithm subject. What is the complexity of map coloring problem is around order of 2 to the power of n, means the complexity is exponential. So the complexity is exponent, and if I tell you specifically the complexity of this graph coloring problem, it is uh, v square plus e. V square means your vertices square plus e, number of edges. So if we'll take an overall, so it is order of 2 to the power of n. So in a map coloring problem, the complexity is very high, which is an exponential complexity of order of 2 to the power of n. To solve these type of problems, we need actually constraint satisfaction problem. Okay. What that map coloring is, let's try to understand the problem first, and then we'll go to the solution. What that problem says, this problem says that suppose that have we have a map. Okay, in a map we have some cities, and in the cities which is there in the figure, this is the figure of the city in Australia, and we have some adjacent cities, and we have some non-adjacent cities. So what this particular problem says, that when we want to color one city, so the same color will not come to its adjacent city. Okay, the same color will not come to an adjacent city. Let's say if I am coloring with the color, let's say red, so this particular red color is not going to come to other city. So what we have to do, the adjacent city, we have to put the adjacent city as other colors. So let's see that. So if we have this city, I am putting the color, let's say red here, and let's say I'll go to another city with let's say the color green. So the adjacent city should not have same color. This is the constraint that we got. Now if we'll see, we have done with red, we have done with green. So which color we have to put here? So definitely we have to put a different color here. So let's say we are putting a different color, let's say blue we are putting. So you can see that all the adjacent city will have different color. So this is called map coloring problem that we have to solve. Now here we have three colors, red, green and blue, in such a way that no neighboring neighbor will have the same color, as I told you. To formulate this constraint satisfaction problem, we have the variable name. Variable name is based on the city name. So we have the city name, right? So what we have city name, Western Australia. We have the city name, which is so we have the city name Western Australia. Here we have the city. We have the city name Western Australia. Northern Territory. Here we have the Northern Territory. Then we have Queensland. Queensland is here. Then we have South Australia is here. New South Wales is here, and Victoria is here, and then Tasmania is here. Okay, so we have these cities related to Australia. Now the graph shows that which are the neighbor of which particular city. Okay. Now let's try to understand this. What are the variable we have? If we'll try to understand what are the variable we have, so you'll see here we have the variable that is x, and we have x, which is WA, which is one city, NT, which is another city, Queens, which is another city, New South Wales, which is another city, Victoria, South Australia, and Tanzania. So these are the variable name. The domain, what domain we have? So domain is red, green and blue. So these variable will be assigned any of the value. The constraint required neighbor region to have distinct color such since there are 9 places where region border. So there will be 9 constraints. So we have 9 constraints. How it is? So it is based on again these values. So we have South Australia. South Australia is attached with Western Australia, Northern Territory, Queensland, New South Wales, and Victoria, right? So if we give the color, let's say we'll give the color to, let's say, blue to South Australia. So you can see any of the neighbor of South Australia will not have the same color. It should have different color than blue. So either it will be have red or it will be have green, but it should have different color, right? So this is how it works. So this is the constraint, this is the variable, and this is the domain that is there in the particular problem. Now let's try to understand how it works. So if you see, so what we are using that South Australia and Western Australia will not have the same color. So it will be denoted as this. SA will not have, means not equal to WA. So how we can write it down? We can write it down in this way. This is constraint, right? So SA comma WA. So SA will not be equal to WA. Where SA is not equal to WA can be fully enumerated in terms of either will have red green or red blue or green red or green blue or blue red or blue green. It means any of the value we can pick up for South Australia and Western Australia, right? Any of the color we can, any of the combination we can pick up for South Australia and Western Australia. So one of the possible solution by taking this constraint satisfaction in mind, this is one possible solution is this. Like Western Australia will have given red, then we have Northern Territory will have given green, Queens will get red, then New South Wales will get green, Victoria will get red, South Australia will get blue, and then we have Tasmania will get red. So in that way, if we are putting the color, so the constraint will be satisfied, all the variable get the value. So this will become a constraint satisfaction problem.